Ravi Gokul is here from University of Chicago, where he's a postdoc. He completed his PhD at the University of Wisconsin in computer architecture, and then he made sort of a hard pivot to quantum computer architecture, quantum computing theories. This is one of the candidate talks for positions in computer engineering. So we'll take it away.
Yeah, thank you, Ravi. Let's see. Great. Yeah, thank you so much, Dirk. And yeah, hello everyone. I'm excited to be here. Yeah, so Dirk mentioned this hard pivot. I don't know if it really is, because I think there's a lot of classical computer architecture opportunity in quantum computing, and that's hopefully what I'm going to convince you about today. I know that many of you here might not have the sort of quantum computing background, but many of the topics I'm going to be discussing are classical themes for the quantum world, and I hope it inspires a lot of you to potentially contribute to quantum in some way or the other. Okay, so I'm going to start with the big picture question. So, what are quantum computers good for? And what are these applications which have so much potential, which has made quantum a hot topic like since the earliest days of quantum computing? So, one application is in drug discovery or accelerating it. The idea is that quantum computers, at least once they mature, can be used to like simulate the molecular properties of drug candidates, and these can be used to accelerate screening processes for drugs, and this can therefore shorten drug development timelines, which was extremely important in the time we are living now. Another application is in industrial chemistry. So quantum computers can be used to simulate chemical reactions, like very complex ones for large molecules, and these can be instrumental in building new materials, fertilizers, fuels, and so on. Other applications include targeting optimization problems in say transportation and supply chain, some forms of AI, finance, security, and much more. And it is these kind of critical applications which have made a lot of both big tech companies as well as emerging startups, as well as some in the Boulder area, and many like national governments to heavily invest in quantum computing. So I'm considering all this potential, I'm going to like give a little bit background on why quantum computers are good at what they do. So essentially, quantum computers are made up of qubits, and each qubit basically has quantum state. Now, a quantum state can be any position, the vector is any position on the sphere, which is known as a block sphere. A classical bit for quantics can take only the values 0 or 1 from the top or bottom. And therefore, essentially, what this means is that a quantum bit is able to be simultaneously in both the classical 0 state and the 1 state, and the weight of each of these states depends on the position of the vector in the sphere. Right? So essentially what this means is that one qubit is able to simultaneously compute over 2 classical 1-bit states, and this translates to n qubits simultaneously being able to compute over 2 to the power n classical n-bit states. And if these exponential number of classical states are sort of manipulated appropriately, then that is when we can get this exponential advantage over classical machines, and this is what is known as quantum advantage. Now, to do this manipulation of these qubits, we need what are known as quantum circuits. And a quantum circuit, like a very basic one, is what is shown over here. And this you can see like 2 qubits over here, and there's a multiple gates acting on them. This thing you see in the blue is known as an entangling gate, and this is what allows these qubits to interact with each other. And these purple squares are single qubit gates, which are rotating the states of each of these qubits along the block sphere, which I showed earlier. And once the circuit completes execution, we do a measurement, and this measurement basically removes all of this quantum state and produces a classical bit string. And hopefully, if you execute your algorithm correctly and your machine was perfect, then the classical bit string you're generating is the correct solution for whatever your complex problem is. Now, there are multiple technologies which are like showing a lot of promise for quantum computing, and they are in kind of different positions in where they are in terms of their promise. But a few of them are the superconducting qubits, which are artificial quantum systems, and then you have natural systems like neutral atoms and trapped ions. So while there are a lot of limitations for each of these, I'm not getting into these. I'm happy to discuss them offline. But the key takeaway is that today we are sort of living in this NIST or noisy intermediate scale quantum era. And what this means is that we have a limited number of qubits, and these are of poor quality, and so we need to keep trying to improve them if you want to make meaningful impact on the application that I mentioned at the beginning. And the other aspect is that as technology continues to improve, some of these limitations will be alleviated to some extent, but they will not entirely go away. So we should learn to live with these things and sort of build stacks on top of it. So the big question we have is that, so we have all these quantum applications with a lot of promise, but we have devices which are imperfect, right? So how do we bridge this gap between applications and technology? Now, on the one hand, we will continue to need a lot of application and theory level research, and what this is expected to do is to reduce the quantum, there is a qubit quantity and quality required for meaningful impact on these applications. On the other hand, you also need improved device capability, so that and which you will continue to achieve, but these are not going to be sufficient to entirely bridge this gap, and therefore we need to look for solutions beyond just the two which I mentioned earlier. But the opportunity, there's a lot of opportunity in using classical principles in terms of bridging this gap between these two areas, and this is where my research focus is. So I've listed some of these areas to the right over here, and you can see that there are topics like compilation, feedback-based optimization, decoding, simulation, cryogenic hardware design, resource management, and so on. So the key takeaway here is that none of these topics are specifically related to quantum, right? These are all topics which you might work in the classical computing world, and they all have significant implications for how you build quantum systems. And that is the main takeaway from this talk is that if you have a background in these kind of classical topics and even some others, you can potentially contribute substantially to the quantum world. And it's sort of these kind of observations which got me interested in quantum computing. So my prior research as a PhD student was in application aware, variation aware, data aware design, the machine learning assisted resource management, approximate computing, optimizing on-chip networks, and so on. And these sort of went across the stack from the circuit level to the architecture to the software level. And this kind of a cross-stack approach from the classical world, which helped me build this kind of a hybrid quantum classical ecosystem to drive towards practical quantum advantage. And I'm going to talk a little bit about these four thrust areas which I've highlighted here. So the first thrust is what I call classical application transformation. So the pie chart you see over here basically represents some application you might want to run on a quantum computer. So there is some portion of the application which is classically intractable, which means it cannot be run efficiently on a classical computer. And this means that if you did run on a classical computer, it is this red portion which you take up most of your runtime, right? And this is why you want to offload this portion of your application to a quantum machine if it is amenable to quantum speed up. On the other hand, this yellow portion, there is no quantum advantage in this, and therefore you don't want this to run on a quantum device for a couple of reasons. One reason is that there is a significant computational cost for running these because these quantum resources are expensive, and the other aspect is that quantum devices are noisy, like I've already described. So in fact, it would be you would end up with worse results if you ran this portion on an application. So in this thrust, I basically focused on preparing different applications so that only the specific portion of an application which can benefit from quantum advantage would be offloaded to the quantum computer. The second thrust is adaptive noise mitigation. So noise mitigation techniques are those techniques which are used to mitigate the effect of noise on your qubits on your quantum devices. Now, there have been many techniques that have been proposed in both theory and experiments, and but these have usually been sort of created in isolation, where the noise which is being modeled on is sort of it's a very specific type of noise, or it is like sort of static. On the other hand, when these techniques are deployed on real devices, the noise is much more complex, or as you say, it varies in wild, and it can also have a lot of volatile components. So the effectiveness of these noise mitigation techniques are sort of limited when you deploy them on real machines. So in this thrust, I have focused on adaptive deployment of these techniques so they can best fit the needs of these these volatile quantum devices, and therefore more effectively mitigate the source of error. The third thrust is scalable error correction, and this is a thrust which is going to be significant when we have these large quantum systems that like thousands of qubits. The idea is that even after you do all this noise mitigation, which I described earlier, it is still not going to be sufficient for nearly perfect qubits. So there is a theme of research known as error correction, where you actually do some amount of classical processing to correct the errors that you see on these quantum devices. Now, unfortunately, there are a lot of bottlenecks concerned with doing this classical processing, and in order to build scalable quantum systems, these scalability bottlenecks have to be alleviated. And this error correction, this scalable error correction thrust, I focused on these kind of bottleneck alleviation techniques. And finally, as I've already mentioned, there are diverse applications and there's diverse technology, and so there is a significant challenge as to identify both the appropriate device to run an application, because these applications perform differently on these different devices, and we also need techniques to boost the fidelity we get from these devices, right? So in this thrust, I focused on better management of quantum resources and better processing of these quantum outputs, so that we can have more meaningful results on critical applications. So these are the 4 thrusts, and from this I'm going to be talking about one project from the classical application transformation thrust and one from the scalable error correction thrust going forward. So I can take any questions now if you have any, or I can.
Yeah, I have a question. So when you're talking about the thrust one, when which you are defining the not Q and free, how can you segregate the program into being Q or not Q? Where will that line be? Like, how can you segregate that?
That's a great question, and in fact, so that is what I think it's a significant theme of research for different applications. It can be pretty different. So I am going to talk about one such application where you sort of do whatever you can first on the classical device and only then offer to a quantum device. But this can vary significantly. For example, if you take applications from molecular chemistry, which is also what I'm going to be talking about, but you can't directly run your chemistry application on the device. There has to be some translation from chemistry to qubits, and then from qubits to also maybe from a logical version of qubits to a physical version of the qubits, and only then do the running on the machine. So all of these are what I call this classical transformation portion, and yeah,
But it's an approximation, right?
not necessarily, because it could be in some cases, but there are many scenarios, again, like the one I'm going to describe, where it is not an approximation at all. Things you do on the classical can be done perfectly on the classical machine before you move to quantum. But it's a great question. Any other questions before I move forward? Okay. Can't see the time over here. Okay. Let it drop from there. 3:44. Okay. Okay, so I'm going to be talking about this work called CAFQA, which is classical simulation bootstrap for variational algorithms. So essentially, variational algorithms are one important class of applications in the near term of quantum. And what we're trying to do is we're trying to use classical computers to find a very good initialization point for these algorithms before they have to be run on these noisy quantum devices. And sort of claim to fame for CAFQA is that even though it's the classical pre-processing technique, the initialization accuracy we achieve using these methods is able to significantly outperform some prior techniques which have been sort of inspired by, this is specifically in the field of chemistry. These have been inspired by some understanding of chemistry and which have been around for nearly 100 years. And CAFQA is able to perform or recover almost 99%+ of the inaccuracy you see in these prior techniques. And this work has both system as well as theory impact. Okay, so the way to think about variational quantum algorithms is basically starting from a classical optimization problem. To consider any classical problem where this can be something like a machine learning optimization, where you're trying to navigate through a contour to find this global minimum. And in order to do this, you are starting from some random initialization point, you follow some gradients, and you try to go to this global minimum. Now, the quantum analog of this problem essentially follows the same path, except that each of these data points in this space has to be run on a quantum computer because it's a classically intractable problem, and these are variation quantum algorithms. Now you can think of this that essentially there is no reason why this should be more challenging than a classical optimization problem, right? But this is made a lot worse due to the presence of noise. Noise causes a lot of issues in how you estimate its objective function, which lead to a lot of these noise-induced local minima, as well as some things called barren plateaus, which means that starting from an arbitrary initialization makes it much more challenging to go to this global minimum. right? So the key insight for Kafka is that even though this is a quantum space, there are actually some data points on this optimization contour which can be efficiently run perfectly on a classical computer. And this is because these particular states correspond to something known as Clifford states, right? And so the theme for Kafka is that we first search through these discrete states on a classical computer and then find best possible among these discrete states and then use this as an initialization point for the variation algorithm. Now, because these are sort of discrete states, we need, and these are sort of exponential in number by themselves, we need an efficient search algorithm to navigate the space, and we use a Bayesian optimization based technique. And once such a good initialization point is found, then in all likelihood, we are able to navigate less portion of the noisy space and therefore are more likely to reach the accurate solution and in quicker time. This is the overview of Kafka. I'm going to get into some of those more specific details on how these variation algorithms work, why are some of these quantum states classically simulable, how to find the optimal solution, and what are the quantitative benefits. So I already mentioned that variation algorithms are these kind of search problems that you're trying to find the global minimum, and this has potential in problems from optimization, chemistry, and multiple other venues. The key idea here is that each of these quantum states is being generated by a quantum circuit, and this is a parameterized quantum circuit. So when you set some particular values for these parameters, they generate a different quantum state, and that corresponds to values on this in this optimization surface. Now there are different ways in which the circuit can be constructed. Sometimes it is application specific, sometimes it's hardware specific, but that is sort of agnostic to the focus of this work. The key here is that the tuning of these parameters is controlled by a classical optimizer, and these different values are producing different quantum states. Now, in the context of Kafka, the key thing to note is that suppose these angles are all set to some arbitrary values, which means like some value between 0 and 2 pi, like you see over here, then this produces an arbitrary quantum state which is classically interactable, and this is why you want to run this on a quantum device. On the other hand, if you choose these angles to be like from a very specific limited discrete set, like these multiples of pi by 2, then these circuits you're generating are actually these Clifford circuits, and there's been like theoretical research for and used in multiple domains to show that Clifford circuits can be classically run efficiently and accurately on a quantum computer. Right? So the goal of Kafka is to generate different circuits like this and search through the space and find the optimum point. Now, the way we do this, as I mentioned, is using Bayesian optimization. And at a high level, this is how Bayesian optimization works. You have an unknown function, this purple line, and you're trying to model this purple line using something called a surrogate function. And once you find a reasonable model, you're trying to find whatever is the target goal, which in this example is this maximum point over here. Right? So, and the way this is done is to make some queries on this purple line, which is this red dot, and you want these queries to be as minimal as possible. Right? So you can see over multiple iterations that this Bayesian optimization approach slowly models, that is this black line slowly models the purple line. And at the end of these 8 iterations, you can see that the surrogate function has well modeled this purple line, and more importantly, it has taken a lot of samples in the region of interest. And this is basically by using something known as an acquisition function, which is selecting which are the kind of points you want to sample, and you can choose to sample more in the regions of interest. So because you've made more samples over here, you can make an accurate estimation of the values in your region of interest. So in the Kafka work, we use this tool known as Hypermapper, which is a tool from Stanford, which is used for both, like in this case, for quantum technique, but also has significant uses in design space exploration in the classical world. And we use a random forest space surrogate model, which is useful in a discrete search space like the one over here. And we use a semi-greedy acquisition function, which means we take more samples in regions of interest and less samples in other regions. Okay, so with this, I'm going to get into some results, and I'm going to talk about the application of molecular chemistry. And over here, the goal over here is to find the potential energy of a molecule for a given bond length, and this essentially means how much energy it takes to break a molecule apart. Right, so over here, I'm going to show VQE, running this VQE, this variation quantum algorithm for like a number of iterations, and you're trying to find this potential energy over here, which is shown by this dashed line. No, because this is a simple molecule, it's lithium hydride, we know this correct answer for classical simulation, but the idea is that you will not know this for more complex problems, right? So now I'm showing you two methods over here to try to find this ideal value. The blue line is using something called Hartree-Fock initialization, which I'm going to describe a little bit, and the other one is the CAFQA initialization, which is this work. So this Hartree-Fock is what I mentioned at the beginning. It's a chemistry-inspired approach where you're making some approximation from the electronic structure of a molecule by restricting what spins it can take. And because you're making these restrictions, that is why this can be run on a classical computer, right? And while in some situations this can be accurate, oftentimes it is not. So you can say that the Hartree-Fock initialization starts at an energy of around -9.6 and converges near the ideal value in like 1,000 iterations. On the other hand, you can see that CAFQA starts almost near the right answer, near -7.8 right at the beginning, and within just like 80 iterations or so, it's already converging to the right answer, right? And so clearly, CAFQA has a significantly higher initialization accuracy and higher accuracy in the end, even though it is not clearly visible. So the takeaway here is that the most important takeaway is that this is not just empirical evidence from this one example that the CAFQA initialization can outperform Hartree-Fock. There is theoretical reasoning as to why CAFQA will at least be as good as Hartree-Fock and usually even better. I can talk more about that offline. But over a multiple molecules that we have looked at, you can see that CAFQA achieves even in just its initialization, it achieves nearly 99% accuracy of this perfect value, which is great, which means there's less to actually traverse on a quantum machine. And it can recover as much as 99.99% of the inaccuracy from this Hartree-Fock approach. And over a variety of molecules, we get like a 57x improvement accuracy. And the Bayesian optimization, which is the classical component, takes around 2,000 iterations to converge an average, which can be different amounts of wall clock time depending on your classical computer system, which is all fine because it is polynomial, right? So the key takeaways of this work: initialization is critical for variational algorithms, especially if you want them to accurately converge on noisy quantum machines. CAFQA initiates this by classically searching for the Clifford space. This is can be done efficiently, and the CAFQA simulation is noise-free, which means that for the initialization point you have no noise. And the search is happening using the Bayesian optimization approach, and overall we achieve 1 to 5 orders of magnitude accuracy, as well as performance benefits over this state-of-the-art search. I'm going to just briefly mention some other work I've done variation algorithms before I move on. So apart from finding and good initialization, you still want to reduce the effects of noise in this complex VQA contours, right? Because initialization, the example I gave you, it took you like super close to the golden star, but that's often not going to be the case. It might put you somewhere over here, right? So reducing the effects of noise is important, and I've pursued multiple approaches to reduce the effects of noise in this variational contour, and I'm happy to talk about these later. So yeah, I'm going to move to a different topic now, so I'm happy to answer any questions right now about CAFQA.
Just a clarification. In your example, noise affects the objective function, but doesn't change the location of the global. Is this an assumption you're making, or is it just for the picture?
Yeah, that's just for the picture. So essentially, the noise can definitely change. So let's say in an ideal noise-free machine, like you got the lowest objective at a value of 3.0. It doesn't have to be 3.0 in the noisy case. It doesn't even have to be this exact same value, right? It might be the case that the noise has completely pushed you out of that energy value itself, right? Which of course then you cannot do any better than what this device can give you. But this value is in fact sort of arbitrary. This is just indicating like the angle which you can take in your answers, which doesn't have any realistic meaning, because the answers is something that there is a circuit which I showed at the beginning, because that circuit is something that you chose to begin with, right? If you had chosen that circuit to be something different, then this 3.0 could have been like 2.0 in some other. So this value doesn't really make any difference. So the real value matters only this energy number, and you're trying to go as close as possible in your initialization. Thank you. Yeah, sure.
So I've got some questions. The first question is, I really like this idea about using the Clifford stackers before looking for non-Clifford stackers. And I'm kind of curious about whether is it obvious that there's certain loss functions for which when you start adding the non-Clifford elements, you will actually get provable reduction in the loss.
Yes, so I think I have it's a great question, and in fact it's an important area in my current research, but I think I hope I have a backup if I think I understand what you're.
Maybe I'll ask a section question too. How do you take the Clifford circuit and then change that or complement that to add on the non-Clifford elements to increase the richness of the variation on stuff?
Okay, I'll give you the first question for Bill. I got the slide and I'll ask you again for the second question. So this is the case where on top of CAFQA, we are adding some non-Clifford elements to the Clifford one. And again, it's only for simple molecules, hydrogen and lithium hydride. It remains to be seen how it will scale. So here for hydrogen, you can see that just adding one T gate to your Clifford ansatz. So the green line is CAFQA here, right? And this is of course over different bond lengths. So you can see that just adding one Clifford, non-Clifford gate gives you substantially improved accuracy over just CAFQA. Now the real challenge is where do you insert this T gate? Right now this is easy again for a small ansatz like this where there are only a limited number of positions. But so this is it's an interesting optimization problem to think about. And similarly, if you look at lithium hydride, again, you can see that this is just with like 4 T gates. Again, we did like a brute force search. In this example, you can see that you can significantly go further. So, so one of the research areas I'm interested in is given a classical compute capability, because some number of T gates can be classically simulated. Depending on if you have like say an HPC system where you're ready to throw at a problem, maybe like a 50 T gate or something you can. So it's like, where do I insert these non-Clifford gates in my circuit and how close can I go to the, so that's a very interesting area of research that we are thinking about. So can you repeat the second question I didn't quite
I think that answers my second question.
Okay, so I think you mentioned something about like the UCCSD, I don't know if you did, but okay, so maybe I'll mention that in this context that there's some interesting work from Virginia Tech on how you can construct an ansatz using chemistry inspired elements, and that is also something we are thinking about over here. Instead of randomly throwing in like T gates, you can throw those UCCSD operators as well. So yeah, great question. Any others before I move on? Yes, go ahead.
Just so I understand, bond length is not a variation parameter for this cost.
Oh yeah, it's not. So this is a different kind of a graph. Yeah, this is usually chemists are usually more interested in these graphs just because the energy differences between these points are what is impactful in terms of chemical reaction rate. So yeah, it is not a variation constant. Right? But this is eventually what you want to plot from the graph I showed you earlier. Right? Yeah, great question. Okay, let's go back. We should make going to the right slide as a quantum problem. Okay, great. All right, so next I'm going to talk about this work, which is completely different from Bayesian quantum algorithm. This is for error correction, which is, as I mentioned, it's sort of long-term goal for quantum computing. And the idea here is that there's a lot of classical processing involved in doing error correction. I'm going to get into the details, but the key insight in this work is that there are essentially 2 approaches to decoding for quantum error correction, and this work sort of combines these in a sort of best of both worlds approach, and it can achieve significant performance gains. And the reason for this is that we take something called a better than worst case approach, which is must be very familiar to people in the classical computer architecture world, which means tackling the easy cases separately in a low cost manner while handling the hard cases in a more like a thorough manner, right? Now, creating this degree of separation means that you're reducing the overall cost of your entire process while still achieving the same results. Okay, so I'll start with some background on error correction. So essentially, we have these physical qubits today, right? So we have these error rates happening. You have errors happening like 1 error every like 100 operations, or maybe in the future you'll have 1 error happening every like 10,000 operations after you apply your fancy noise mitigation technique and so on. But a lot of these applications require like error rates which are more in this range, like 1 error every million or trillion or whatever this 10 to the power minus 15 is, right? So you need like really low error rates. And this is sort of tough to achieve with just these noise mitigation techniques. So this is where like quantum error correction comes in. The idea behind error correction is that each physical qubit is encoded with redundancy into multiple qubits. And the idea is that at any point of time, only a few of these qubits are suffering errors. And so you can use some classical crossing to correct these errors and thereby create the logical perception of a qubit which has those very low error rates. Right? This all seems fairly simple, but this becomes really challenging in the quantum world because it's very challenging to find out which of these qubits have those errors. Because in order to find that out, you would want to observe or measure these qubits. And if you measure these qubits, they're going to lose their quantum state. And you definitely don't want to do that because you're still performing quantum computation. Right? And this therefore results in there are some intelligent ways to get around this, but this results in your decoding process becoming very complex, and you have to solve these complex graph problems on your classical machine. Right? So, and therefore, this is a big scalability problem, and therefore, there's a lot of classical computer architecture research opportunity over here. So, to set the scope for this work, we're interested in cryogenic quantum system, and the setup is like you have a dilution refrigerator where you have your qubits maintained at like a 20 millikelvin temperature, and then you have some classical control happening at 4 Kelvin, and then other general processing stuff is happening at room temperature, which is like 300 Kelvin. Right, so I'm going to explain this with an example. So let's say you have 5 logical qubits at this 20 millikelvin domain. Like what I mentioned earlier, each of these logical qubits is represented or is encoded in many physical qubits. Now the traditional view to the error correction decoding is that you have these qubits producing errors. These errors flow all the way from this cryogenic domain to the room temperature domain. And over here, you have these complex decoding systems performing the graph, like solving those graph problems. And then you send the corrections back and fix those errors. Right? But the issue here is that the bandwidth required for all of this to happen runs into like terabits per second for practical application. And this is because the latency with which the decoding has to be completed is like can be like 1 microsecond or so, and this is a functional correctness issue. This is because if you don't correct these errors in time, you're going to have new errors and you're going to create a backlog which can never be overcome. Right? So you want to correct errors quickly. This leads to this huge bandwidth issue, and this bandwidth is a bottleneck over here because you have these sparse metal interconnects between this 4 Kelvin and this 300 Kelvin domain. So this is a huge scalability challenge. On the other hand, there has been some more recent works in the sort of doing decoding in the cryogenic domain. So what this means is that you're moving your decoders from this 300 Kelvin to this 4 Kelvin temperature by implementing like cryo-CMOS or single flux quantum logic. Now the bandwidth bottleneck is alleviated because you don't have to use these interconnects for doing this decoding, and you have much better like bandwidth supported by these superconducting wires between these temperature domains. But the big issue here is that the power budget for this kind of a cryogenic domain is only around like 1 watt, right? And at 1 watt, you cannot decode a sufficient number of logical qubits which is needed for practical applications. So again, scalability problem. Okay, so how do we solve this? So what I've shown you so far is essentially these 2 schools of decoding. So in one case, we have this sort of off-chip bandwidth constraint approach, and the other is this cryogenic resource constraint approach. But the commonality between these 2 methods is that you have a single decoding system to decode and correct all the errors which are flowing from your qubit. So it's a one-size-fits-all approach, right? And it is this sort of a one-size-fits-all theme that we are breaking in our work. So what we identify is that the stream of errors can easily be separated into trivial errors and complex errors. Okay, and so the quantum reasoning behind this is that suppose those logical qubits which are represented by the many physical qubits, suppose they have errors which are isolated, then, and this is by the common case, I'll get more into why this is so, then these can be decoded very easily by some very simple decoding techniques. On the other hand, if these errors form a chain, and this is the rare case, then this is when it's more complex to decode and why you need your sophisticated decoder. So once we know how to do the separation, we have all of these trivial errors being decoded by a very lightweight decoder, which we call the click decoder, which sits in the cryogenic domain, and only these few others have to go off to your complex decoder. Right, and going back to this system level view, what this means is that now these errors are represented by T and C to indicate trivial or complex. All trivial errors are taken care of by this click decoder over here, which is satisfying your power constraints at this domain for like even like millions of qubits. Whereas only these few complex decodes have to go off chip, and they are handled by this complex decoder. And your bandwidth bottleneck is also alleviated because it's only a very small percentage which have to flow off chip. Right, and by doing both of these, we are able to significantly improve the scalability of these cryogenic QEC systems. So in the next few minutes, I'll go into some details on how exactly quantum error correction works and why all of this works as it does. And the next few minutes can get into a little more quantum detail that people might be comfortable with, but it's fine if you've understood the high level idea which I presented over here. So I'm going to be talking about surface code, which is one kind of a quantum error correction code, and this is especially attractive in the near term of quantum computing for multiple reasons, and I can talk about that later. The idea is that, so one logical qubit is encoded in d squared data qubits, where d is something called the code distance. So you can see d equal to 3, so 9 data qubits over here. Now, then you have something called ancilla or parity qubits, which are the other qubits in green and blue. And these qubits are used to sort of get some estimations of what are the errors that are going on in these data qubits. And the reason why we need this is because, as I mentioned earlier, we cannot directly observe these data qubits to find out what errors they have. So we have these other qubits, and the way this pattern works is dependent on the surface code, some theoretical method. So let's say we have an error on this data qubit D right in the center. And a particular type of error, which is, you have two kinds of errors, X and Z's, and not getting into the details of that. But what happens when you have this error on this data qubit is that these two qubits, these two X's over here get triggered, and this yellow triggering is known as an error syndrome. And then it is these syndromes which are visible to a complex decoder, and then the decoder knows that it's this data qubit in the middle which is errored, and therefore can issue a correction. Right? Fairly simple so far. Yeah, I should also mention that as you increase the code distance, the size of this lattice will increase, and it means that you need more physical qubits, but your the kind of error rates you can achieve reduces, which is great, but your kind of decoding overheads increase as well. So that's the kind of trade-off you need to think about when you're choosing your code distance. So I also want to mention what happens when you have a string of errors, because this is sort of part of the intuition as to why some decodes are more challenging than others. Let's say that you have a sequence of 3 errors that you see over here, the ones in red. You can see that the error syndromes are being triggered on only the X1 over here and X4 over here, right? X2 and X3 are not triggered. And the reason for this is that so DA will trigger X1 and X2, and these work by triggering, I mean bit flips basically, right? So then by DB will trigger X2 and X3, DC will trigger X3 and X4. So basically X2 and X3 are triggered even number of times, so that gets cancelled out. So essentially, you can see that when you have a chain of errors, the syndrome information is generated in a very limited manner, which is what sort of makes decoding more complicated. Okay, so with that intuition, I'll go into some more details. So, so 2 things I mentioned earlier was that isolated errors, which are the ones which are easy to decode, are the common case. So why are they common, right? And this basically just stems from some very simple math, and I'm going to show this for a logical qubit which is encoded in 49 physical qubits, like you see in this lattice over here. So the probability that there is just one data qubit over here which has an error, if you do the math for this system, where the physical error rate of 10 to the power minus 3 is around 5%. That means given this lattice, there's a 5% chance that there's an isolated error over here. Okay, so it's fairly common. On the other hand, let's say the shortest chain of errors, which are these 2 diagonally adjacent errors. Let's say you have this chain anywhere in this lattice. The probability of this happening is like 0.03%, or like 160x less likely than the example I showed earlier, just pure math, right? So it's clear that if I had a method to easily handle the other case, then I would need to do this only like 1 by 160th of the time, which is the whole thing also. So this is fairly easy, but the more interesting point is why are isolated errors trivial to decode, right? Which is the other aspect as to why can we use a click decoder to do it. And for this, I'm going to like sort of work out a small exercise. So let's say that you see only these two syndromes triggered, which are shown as 1 and 2. Can you identify which are the data qubits, the chain of data qubits which could have caused these errors? I'm going to give the answer because there are multiple solutions and it's not working. It's not completely solved trivially. So let's say that this is one possible chain which have caused these errors, right? So you have these 4 data qubit errors, A, B, C, D, and they have triggered these 1 and 2. So let's say that you did solve this. So how would you have solved this? You would have potentially tried out like different patterns of data qubit chains, and you would have done like a maximum likelihood estimation as to which is the most likely one which will cause the sequence. And your final solution might have been this red sequence over here, because the red sequence is triggered by just 4 errors, whereas this pink sequence is triggered by 9 errors. And just by those probabilities, this 4 errors is much more likely to be than the 9 error case, right? Now, this is exactly what your complex decoder is solving. It is essentially trying to find the shortest paths to complete these error patterns, and this is why those complex graph problems come from when you sort of have to do this global. On the other hand, let's take a simple example where, or it's not simple so far, but let's take an alternate example where you have these 2 syndromes triggered over here and these 2 syndromes over here. Now, can you identify which ones have the errors in this case? Some of you might have, because this is an easy one, you will end up with the A error, data error between these 2 over here, and the B data error between these 2 over here, right? And this is by far the common case. Now, the key aspect here is that in order to find out that this A had the error, you did not have to look at this entire lattice. You could have known that this A had this error just because these 1 and 2 errors were diagonally adjacent to it. And similarly, you would have known B had the error because 3 and 4 were diagonally adjacent. So the key aspect is that you could have been agnostic to the rest of the lattice to figure this out same way over here, right? And this is exactly how the click decoder works, right? Each unit of the click decoder only looks at these smaller regions of the lattice, and each of these errors gets decoded independently, and that's why this is becomes a simple decoding for these kind of isolated errors. Right? There are some additional subtleties that I'm not talking about. One is that you can have like measurement errors, which complicate this process a little bit. And then there's also a need to verify if these triggered syndromes are caused only by these kind of isolated errors, which is tough to explain, but also very easily can be handled. Right? So essentially, your click decoder is made up of multiple such units of these click units, where each of these click units is only targeting a very localized region of this entire space. And each of these units only takes up like 10 combinational gates to implement, therefore it's very amenable to like building in the cryogenic domain. Number of such units scales as d squared, where again d is the code distance, and it is in fact linear, the number of physical qubits, so very favorable scaling as well. Okay, so with that, I'm going to discuss some results. So first, I'm going to talk about off-chip bandwidth reduction, which means how much I'm reducing the bandwidth that we have to go off-chip to the complex decoder. Right, and I'm showing this for different physical error rates, with physical error rates decreasing from left to right. You can see that in all of these scenarios, nearly 90 to 100%, it's not exactly 100, but almost 100% of the errors can be handled by the click decoder. And the reason why this is the percentage is increasing is because as your physical error rate reduces, there's even lesser possibility of those chains happening, right? And as a comparison to some recent prior work in the quantum architecture community, this method is achieving 10 to 10,000x greater bandwidth reduction than other techniques, which is compressing data, which has to be sent entirely offline, because compression becomes tough even if you have like a few non-zero bits. The other aspect is that because of how lightweight that logic was, they are able to implement this in the cryo domain with, in this case, use like the SFQ, single flux quantum logic. So we are able to support for like a 1 watt power budget, we're able to support like 2.5 million qubits. And if you, depending on what your physical error rates are and what's your logical error rate target, this can correspond to like 1,000 to 10,000 logical qubits, which means it's useful for practical application, right? And compared to some other cryogenic work, where this is what I described earlier, where you're doing all your decoding in the cryogenic domain, at a code distance of 9, click uses like 20 to 25 to 80x less resources. And this will only improve when you go to later, larger code distances, because as I mentioned, the click decoding is linear number of qubits, whereas these other ones they scale. The scaling is more complicated, right? So benefits in both bandwidth as well as resources. And the takeaways are that there are severe bottlenecks to PLC decoding in terms of bandwidth, area, power, and so on. We take this better than worst case approach, which separates these into two classes of decodings, and this can significantly alleviate these bottlenecks. The benefits we achieve are like 2 to the 4 orders of magnitude greater than prior work. Okay, so I'm going to next move to some my research vision and future steps. I'm happy to take some any questions about this work.
The numbers you just presented today for quantum memory or for quantum computation?
Yeah, great question. So this is all for quantum memory. So right now we are doing some work where how we would do something like lattice surgery on this, because it is possible, but it requires some ability for click to handle like different code distances when you're doing like merge operators and so on. But yeah, this is for quantum. Any other questions?
I think I missed the. What is it again that the complex errors are less?
Okay, so that's
I didn't see the like the location of the.
okay. So
Part of.
okay, so complex errors are firstly ones which are error chains, right? And the reason why these are challenging to decode are because you essentially have less syndrome information. So let's take that at face value. Now the reason why error chains are less common is just because of the probability, right? For now, just to have like 2 errors occurring right next to each other, the probability of this is I mean if you it's like a multiplicative of those 2, so which makes this significantly less likely than one random error occurring. Anyway, so that's it. So just doing that, the probability of this is like and the lower your error rate is, the lower, because the chains are multiplicative in their problem. Yeah, go ahead.
Do those errors have to be correlated with to be a chain?
It depends. I would say that they could be, it doesn't have to be, because sometimes the way these errors are occurring are, it's almost the way like, so I mentioned the way surface codes, this thing over here, right? So what's really happening is that, what I didn't explain is that these errors are not actually discrete. They are actually like, there's a continuous decay in each of these qubits, but when you do this measurement step, which gets these results on these qubits, you're actually discretizing those errors. Okay, so which helps in error correction, but also means that there's a probabilistic nature to whether error discretization happens or not, right? So which means you can have adjacent qubits having errors just because they happen to collapse that way, right? It doesn't have to be correlated, but it is the case that there will definitely be correlations when you think of this circuit model, right? Because if you have like an entangling gate, it's more higher likelihood to get an error, which means the 2 qubits might have error. Right? So both are true. There was one more question, I think.
No, he asked the same question.
Oh, okay, great. Okay, so I'm going to quickly go through some research vision and next steps. So in my future research, I'm planning to like break my research down into 3 classes: gray box optimization, resource diversification, and NIST, that is the current day system to fault tolerant to future system migration. So gray box optimization is the idea that quantum machines even in the future are still going to suffer different forms of noise, and we will never totally understand why these noises occur and when they will occur. Right, so you want to have a class of techniques which are sort of mixing theory as well as empirical evidence to design techniques to correct these errors, and you want these techniques to be scalable as well, right? And there's multiple avenues of research in this domain. For example, there's ideas for using classical simulation, like similar to CAFQA, but expanding on the CAFQA work I mentioned earlier. I have some collaboration going on with already, but I think there's also potential. I know like there's a lot of HPC interest in Boulder, and I think using that in more these simulation techniques would be great. Then there's interest, potential to optimize these techniques in the context of specific applications like wireless networks, and again, multiple potential collaboration, some prior work as well as collaborations over here, both in wireless communication as well as physics. Then there's in general need to build more scalable quantum software. A lot of quantum software we have today have been opportunistic because the quantum systems are very small. But essentially, we need to build larger systems, so we need to find efficient ways to do this, and other techniques such as application to quantum sensing, practical deployment of different noise mitigation techniques, and in general, better optimization techniques. Right? Some of the techniques described might be naive, but there's some levels of sophistication we can add to just building these optimization techniques themselves. The second axis is resource diversification, and what this means is that in the cloud, we already have today multiple kinds of quantum computers available, and this diversity will only increase in terms of each of these kinds as well as across different technologies. Right. So, and we want to find good application specific and technology specific methods to make the maximum out of these devices that we have so that we can really push quantum. Right, and there's again multiple optimization, multiple research potential over here. Like management in the cloud is a very interesting area, lots of opportunity, and it's a very nascent area of research. Again, there's a lot of cloud research which is of interest over here, so potential collaboration over there. These ensembling methods, which I don't have time to talk about, but it's a very exciting area of research. Happy to talk about that offline. Then building scalable hardware software stacks for different kinds of technologies. A lot of the work in the past few years have been on superconducting devices, like from IBM and so on, but there's a lot of opportunity to do these for like trapped-ion systems, neutral atoms, and so on. And in the future, also ideas like security in the cloud, once the applications we start running are actually meaningful. And the last class is a migration from the noisy devices we have today to futuristic quantum machines. And what this means is that we have a wealth of techniques in the last 5 to 10 years, which have been optimizing, like in terms of compilation, error mitigation, early stage quantum error correction, and so on, which have been great for the machines we have today. But many of these techniques are not going to easily scale in the future when we have like 10,000 qubit machines, which need fault tolerance for some of those huge applications like factoring and so on. So, and we don't want to view these as two discrete entities because they are in fact a continuous spectrum. So we want to find ways to seamlessly migrate from today into the future. And some of these techniques over here are like the resource ensemble, which I said was very interesting earlier, but I didn't describe. There's an equivalent over here in the quantum error correction world as well. Then there's potential for improving decoding in the context of non-uniformly noisy system by understanding more about where exactly this noise comes from. Quantum decoding should be hierarchical because quantum systems can be hierarchical, a lot of potential for research over there. Then other optimizations such as just linking the two areas of the two topics I spoke about over here, variational algorithms and error correction, potential intersection for these topics, and topics like partial error mitigation and partial error correction. So in summary, so my work is basically been about as a classical computer architect, how I can influence the quantum world. And I think there's a lot of potential to contribute, both in the near term as well as the long term. And before I conclude, I want to talk a little bit about some outreach and what I can make contributions, not just technically, but also maybe use these technical platforms to contribute to the sort of wider community. So I created this workshop known as I Took in Quantum as a mentoring workshop to enable more people from the students, especially from the non-quantum world, to find areas like what I've been talking about this entire talk, right? So this is just a program we had from a couple of years ago where we had like multiple topics, some of them which is so well based on their own classical computing research that I don't know enough about, like service chaining, for example. You don't know what that is. But so the point is that there's a lot of potential to take these topics and get students involved in the quantum world. And so while I continue to do this in the context of conferences, I also want to do this in a more DEI focused expansion of these kind of methods and other mentoring approaches, both within University of Boulder and in the community over here. And I think some way to do that is through undergraduate mentoring. The mentoring program I mentioned earlier is kind of like a 1-month program, which is good, but not significant to really do significant outreach. I think doing long-term undergraduate mentoring is a great way to get more students involved, both in computing in general and quantum in specific. I also have interest in building these introduction to quantum programs for high school students and get involved in in area of maybe get them excited to just come to undergraduate school and then hopefully go to graduate school, working with more diverse student and professional bodies, because there's lots of scenarios where these kind of more emerging technologies are sort of lost in the underrepresented communities because they are less aware of some of these advancements and want to work. And I know that many of these institutes have like student bodies in this university as well. And of course, I also want to, as an international student myself, but postdoc now, but I'm especially empathetic about getting like international graduate students involved, because again, it's a lot of the cases where you don't have as much exposure to this in other places when you come to a university over here. So with that, just my acknowledgements. All of this work is done through extensive collaboration across multiple universities and researchers across the stack, which is very important to make practically important impact on real applications which matter. And with that, I will conclude, and hopefully I have a few minutes. Thank you. Any other questions?
So, you presented this application of error correction, in which you separated the handling of the simple
Yes.
cases from the complicated. You placed one in the cold area, and one in the.
Yes.
What do you make sense to have both of them in the cold area?
Yeah, great question. So, not necessarily all in the cold area, but what we are working on is a multi-level hierarchy where, so I mentioned like the 4 Kelvin domain, which is suitable for like a single flux quantum. There's also like a 37 Kelvin domain, which is usually where like cryosity mass logic is more suitable. So one of the things we're thinking about is that we can have at least a 3-level stack where click does what it does at 4 Kelvin. Then you have an approximate or like one more level of decoding happening at the priority mass 37 domain. And the advantage of that is that there is potentially for techniques like power gating in cryosity mass, which means that it doesn't have to dissipate power unless it's in use. Otherwise, there is no point in using it, right? So, and it's only even fewer errors that have resolved it, and that's really important because when I talk about a million qubits over here, right? And of course, there's operations, and let's say it's 10,000 qubits, right, or 100,000. But if you need to go another order of magnitude, you will need a 20 higher. Great point. Yeah.
Yes, so when we're talking about error propagation, like how does it physically propagate? What is an error productivity?
Oh, so are you talking about the error which is happening on the qubit or an error?
At the qubit.
Okay, so great question. So let me go back. Fine. Okay, yeah. So let's look at this very simple circuit, right? So what is happening here is that you are applying some gates, and each of these gates is basically moving this on that block sphere that I showed you earlier, right? But what happens over time is that the state is decohering, right? Which means you're losing the perfect, and there are many different ways in which you can decoher, right? And similarly, so there is some decoherence which is happening just over time over here. And also some effect of that happening when you're applying these entangling gates. Because when you're entangling gate, what's really happening is that, so what are these gate operations, right? This is a level of abstraction. You're essentially applying something like microwave pulses on your qubits, and these pulses are not perfect. So which means that when you're hitting different qubits nearby, there is some like resonance related issues and so on, which causes some parasitic coupling and those kind of issues, which will further worsen the state of these qubits, right? So it is sort of that kind of an analog or continuous error which is happening. But so when you're doing noise mitigation, what you're doing is that you're correcting for these analog errors themselves, which I didn't really talk about over here. But what it means is that let's say that your error is a pi/4 error, just for argument's sake. Now, if I put another pi/4 over here, which means that I can technically cause a yeah, well, not as, or yeah, you can. There's something known as dynamic decoupling where you're essentially reversing the drift so that you can cancel it out. On the other hand, when you're doing error correction, it's different because what you're really doing is you're, as I was mentioning for other questions, you're discretizing that error. So when you do that measurement, which is yeah. So yeah, so every clock cycle you're doing there are some operations which are going between these qubits. And so even though the continuous error over here might be like some let's say pi by 6, right? So what will happen is that with some probability, this error will collapse to 0, which means no correction is needed, which means this will not flip, right? On the other hand, with the remaining probability, this will collapse to a pi by 2, which means there is an error, and that means the correction has to happen. Now, the key thing is here is that the pi by 2 is not just an arbitrary, it is specifically that the way the error correction works, this will only flip to a pi by 2 on the x-axis or a pi by 2 or on the z-axis. That's why these correction can be done classically, right? Because what does it mean if you suppose you have deviated by a pi by 2 in one direction? That means the correction you apply is another pi by 2 because that you're essentially creating a pi chain. So yeah, so the way it discretizes is different over here.
So the click decoder is basically always monitoring all the variations and it can basically find out if there is a change.
Yes, so the click decoder is taking the errors which are coming out of these qubits. So any decoder, okay, this is true for any general decoder that discretization has already happened. So that is part of the quantum error correction code, right? And there are different codes which can sort of work in different ways. But everything the decoding does is after that level of abstraction. So the continuous aspect is completely lost on these guys. Yeah, great question.
Let's thank our speaker again and let people who need to leave go.